let's begin our journey into knowledge representation and reasoning, a foundational pillar of artificial intelligence. These concepts are crucial foundations for building AI systems capable of intelligent decision-making. Now, let's delve into the very core of knowledge representation and understand its fundamental principles. This involves how we effectively represent information so AI systems can process and utilize it. First, let's define knowledge representation as a field within AI, focusing on how we represent information. It's essentially the field of AI dedicated to representing information about the world in a structured way. Understanding its importance, we see it's crucial for AI to tackle complex tasks effectively. Indeed, knowledge representation is absolutely crucial for AI to solve intricate and complex problems. It also greatly facilitates data understanding, allowing AI to make sense of incoming information. This helps AI systems interpret data meaningfully, transforming raw data into actionable insights. Furthermore, knowledge representation enables automated reasoning, a key component of intelligent systems. It supports AI's ability to make informed decisions based on the knowledge it possesses. Today, we'll explore propositional and first-order logic, two fundamental forms of reasoning in AI. These are the two primary forms of logical reasoning that underpin many intelligent AI systems. Let's start with propositional logic, a simpler system for representing true or false statements. It deals with propositions, which are declarative statements that are definitively either true or false. Propositional logic uses logical connectives, like a ND or OR, to combine these simple propositions. For example, "It is raining" can be represented as a proposition, perhaps symbolized by P. Next, we have first-order logic, a more expressive system that builds upon propositional logic. It extends propositional logic by introducing objects, relations between them, and quantifiers for greater detail. This allows us to express complex relationships and make broad generalizations about the world. An example is likes John, ice cream, which shows a relationship between John and ice cream. Let's now explore logical connectives and quantifiers, essential tools for building complex logical statements. These elements are crucial for constructing intricate and precise logical statements in AI. We'll begin with propositional logic connectives, which combine simple statements. The ND connective, denoted by the symbol caret, means both statements connected by it must be true. The OR connective, symbolized by the wedge, means at least one of the connected statements must be true. The NOT connective, represented by the negation symbol, simply reverses the truth value of a statement. The IMPLIES connective, shown by an arrow, means if the first statement P is true, then the second Q must also be true. The BICONDITIONAL, indicated by a double-headed arrow, means both statements are either true or both are false. Moving on, let's discuss first-order logic quantifiers, which express quantities of objects. The universal quantifier, represented by an inverted A, means for all members within a specified domain. The existential quantifier, an inverted E, signifies there exists at least one member in the domain. These powerful symbols enable us to express general and specific statements about various objects and entities. Today, we'll compare propositional logic and first-order logic, two fundamental approaches in AI reasoning. We'll explore the key differences between them and understand their roles in various AI reasoning tasks. First, let's consider their expressiveness, which refers to what each logic can represent. Propositional logic, or PL, is less expressive, primarily handling simple facts and their conjunctions. Next, we'll look at the computational complexity associated with each type of logic. PL is generally computationally simpler, making it efficient for specific problem-solving scenarios. Finally, let's discuss the practical applications where each logic truly shines. PL is ideal for simple rule-based systems, while first-order logic excels with complex relationships and entities. Now, let's dive into the different types of logical inference, how we draw conclusions. These methods are all about how we derive new knowledge by carefully analyzing known facts. Deductive inference means the conclusion must logically follow directly and necessarily from the given premises. Inductive inference involves generalizing broader rules or patterns from a set of specific observations or instances. Abductive inference focuses on finding the most plausible and best explanation for a given set of observations. Let's explore the resolution method, a powerful technique used for automated theorem proving. The first step is to convert all your logical statements into conjunctive normal form, or CNF. Next, we negate the goal, or the conclusion we want to prove, assuming it's false. Then, we add this negated goal as an additional clause to our set of existing clauses. We systematically apply the resolution rule to pairs of clauses, generating new resolvent clauses. The process continues until we find a contradiction, which is an empty clause. If a contradiction is found, it means our initial assumption was false, and the goal is proven. Now, we shift to probabilistic reasoning, a crucial approach for handling uncertainty in AI. It allows us to update our beliefs and make informed decisions using Bayes' theorem. At the heart of probabilistic reasoning is the fundamental and widely used Bayes' theorem. The formula is P of a given B equals P of B given a times P of a divided by P of B. Here, P of a given B represents the posterior probability of event A occurring, given that event B has happened. P of B given N is the likelihood, or the probability of event B occurring, given that A is true. P of A is the prior probability of event A, our initial belief before any new evidence. And P of B is the marginal likelihood of event B, the total probability of B occurring. This theorem is core for effectively handling uncertainty and making decisions in AI systems. It allows us to dynamically update our probabilities and beliefs as new evidence becomes available. Bayes' theorem is essential in fields such as medical diagnosis, spam filtering, and risk assessment. All right, class, we've covered a lot in this session. Let's now summarize the key concepts we've learned. Here are the most important takeaways from our discussion on knowledge representation and reasoning that you should remember. First, remember that knowledge representation, or KR, is absolutely vital for AI to understand and effectively use information. Next, propositional logic is excellent for handling simple true or false statements and their logical connectives. Then, first-order logic extends propositional logic by introducing objects, relations, and quantifiers for richer expressions. We also explored inference methods, such as deductive, inductive, and abductive reasoning, to draw meaningful conclusions. Remember that theorem proving helps validate logical statements, often using powerful methods like resolution. Finally, probabilistic reasoning is crucial for addressing uncertainty, utilizing powerful tools such as Bayes' theorem effectively.